Alright, we should be good. We're back. We're back live. Back designing this ping pong ball shooter. I believe where we left off not yesterday, on Friday, we were ranking these different types of mechanisms that we could potentially use for a ping pong ball launcher or shooter. We were discussing, lastly, was the catapult design. We just have an arm that retracts, or I think we changed the design to something like this because it's easier to build. So essentially what we have is a ping pong ball that carries a ping pong ball, and then we move basically this track up and down, and then we also rotate the whole thing to give the swinging motion to launch the ball. So I think that's what we redesigned the catapult from. Originally we had more of a truncating design, or a design that progressively got longer to extend the arm, which therefore would control where the ball would be thrown and so forth. So I think that is a better design. We also discussed changing this spring-loaded shooter instead of using this whole mechanism right here. Sorry, let me change the pixel size. So instead of using this mechanism right here, we realized that we could just exchange that for a solenoid, or like a piston, electrically controlled piston, which is a lot simpler than using a motor and a string and some sort of pulley and then a spring mechanism, and then we have to reload and load the mechanism, which is way more complicated than just using this as just a solenoid. So I kind of like the solenoid idea. The only problem that I have with the solenoid is that I'm not sure if we could vary the speed of the solenoid, meaning the stroke length of the piston. So the reason why I want to vary the speed is because we could vary the distance that the ball can be thrown. So if you could vary that, I think this would be a very clean design, because then all we have to do is put like a tube over here which guides the ball, and then it'll be launched. So I think that would be a very nice and simple design, like really nice and simple. So I really like that a lot. So we might actually change this rating from a 4 to something more comparable to the tennis ball shooter. So there's that. And then, so I guess we'll just continue from where we are left off. So essentially what we're doing now, if you guys are new here, essentially what we're doing, we went through the whole, we defined several design criteria, and then we went through each one, came up with ideas. So that's what all this stuff is. We came up with all these different ideas. We came up how we're going to control the robot through the internet using some sort of Twitter, Twitch, or YouTube API, so that we could interact with it over, a live stream. And then we went over the different kind of shooting mechanisms. We came up with 6 different ones. We rated 4 of them. We still got 2 more to go: the pump air shooter and the gravity shooter. And then we also went over how we're going to do the live video feedback, what potential things that we might need or will need. We also went over the different power sources. Sorry about this. I realize it should look like, there we go. That should look a little better, hopefully. So we went over the different power sources. This is going to be a stationary device, so I really believe we're just going to use a DC power supply. There's no reason to make it wireless. And then we also went over the ideas of how to store the ping pong balls, like how we're going to reload or just load the ping pong ball launcher or shooter. So we came up with 2 different ideas, using a reservoir, basically a bowl, and then gravity feeds into the launcher, or we use a spring-loaded clip. We just use a spring to just push a ball up to the position where it needs to be and then launch it, and then just repeats the action since we have a spring. We also went over the different sensors. There's a lot of different sensors what we can potentially use depending on what design we choose to go with. And then position control. This is how to control the position of the of the gun, not gun, the ping pong ball shooter or launcher. Um, Basically, we need to orient the launcher horizontally, so there's some sort of rotation this way and then some rotation this way, so that way we get uh, all positions controlled, I guess. And then for later features, we have AI and PC playing ideas. This is again way later on in the project, but let's say if we don't want to do this over the internet, we could just have this robot play against yourself, I guess. Came up with different ideas how we're going to do that, what other features might be useful or make the game more fun. And I believe that's it. So, that was a brief overview of what we did. So going back to here, we'll come back to the spring-loaded shooter in a bit. I think we should just finish up these last two so we could finally choose a design or a mechanism. Okay. So the pump air shooter. So how this mechanism works, just to refresh everyone's memory, essentially what we have is a pump. I drew it as a hand pump or a push pump. I don't know what you call this, but essentially we pump air into a vessel or another reservoir, and the reservoir is closed off, meaning it could store pressure. We basically store pressure, whatever amount of pressure we need to vary the length of the ball being thrown. We store that precise amount of pressure, and then we release the valve. We control the valve probably electronically, and then that will send the air coming out, and that air will push the ball. This is a check valve. If you guys don't know what a check valve is, it just prevents a one-way of flow. Hey Dane, no worries. You're actually pretty early. We just got started, so thanks for coming. So yeah, a check valve just basically prevents air from going, or allows air to only go one way, I should say. So there's that. So how we're gonna do this? To be honest, this is no different, in my opinion, from the fan shooter. And the reason why I say that is because the principle is practically the same. It's just the only difference is how we're gonna basically move the air, right? I mean, here we have a fan. Here we have a pump to store pressure. A cool thing about this is that we could load a ball whenever we want, as long as the valve is closed, which is a better design than here. Because last time we were thinking about why the fan shooter would be a difficult design, and it's because we need to place the ball at a specific moment to even have the device work properly. And the reason why I say that is because we need to vary the speed of the fan, right? And the ball needs to be launched at a specified distance, or whatever is determined by the user, right? And if we put the ball in place, and right here, if we put the ball right there and then turn on the fan, there will be a minimum threshold at which the fan speed will start increasing the ball's movement, if that makes sense, or the ball will start moving at some minimal threshold. And that can be an issue, because if you want to launch the ball at a specific fan speed, we won't be able to do that. So what that means is we need to get the fan speed up first, and then put the ball where it's supposed to be, so it can be launched at the correct speed. Hopefully that makes sense. And this design makes that simpler, is because we have this valve here. That means we can store the pressure, all the pressure we need before, regardless of where the ball is, if that makes sense. So that's a plus in this design. I don't know what you would categorize that as. Convenient? How do you say it? it's just a better, or it's not ball dependent or ball location dependent, which is a plus. I swear this page is gonna be so cluttered by the time we're done. No ball location dependence. So that's a plus. I think that's a plus. That may be an issue, but as far as I see it, it's a plus. So another thing, I've been Great Dane. Nothing much has changed recently. I just had a pretty casual weekend, you know, just hanging out. Nothing much, nothing too crazy. How about yourself? I don't know. What have you been up to? So besides that, we don't have to use a hand pump. We obviously don't. That's because we could just use any other pump, really. We could use an electric pump, air pump. Yeah, we don't have to use this hand pump, so that's just for pictorial purposes. Yeah, no problem. Besides that, I mean, it just adds an extra step that we might have to worry about. I mean, leakage might be, in a practical sense, leakage of air can be an issue. If the valve is not placed on properly, if it's not, or even the check valve is not placed on correctly, that could be an issue. We're just leaking air. Over time, I'll probably do that, depending on what we use for the vessel if we choose this design. So that might be an issue. So air leakage, I guess. And the fan shooter doesn't have that problem because it's a fan. It's supposed to leak air to push the ball. So air leakage can be a con. What else? We have besides that, I mean, it's no different from the fan shooter. Is it better designed than the fan shooter? I'm not sure. If you guys have any input, just let me know. I'm open ears for all this stuff. I'm just winging everything. I'm just thinking out loud. So any input is great if you guys want to input. To be honest, I want to just start like 3D modeling. Just start designing this thing. Just start getting into the technical details, but it's gonna be some time. Hopefully by the end of this week we get everything situated and ready for some actual design and some building. Yeah, I mean, I don't see what else could be an issue. I guess controlling the pump. Oh no, you just turn it on, I guess. Controlling the valve, will probably use some sort of. I'm pretty sure we have like online. There's some sort of valve you can control electronically. I said there's 2 motors per joint. I'm referring to the catapult. 2 motors per joint for a simple arm. I don't know what the second motor is used for. Maybe that's... Yeah, I'm not too familiar with robotics, but if they say 2, I mean, I guess they use 2. I'm not sure why they need 2. I mean, I could think out loud, but I don't know why. Maybe to offset? Yeah. Like, some things you just are surprised about when you learn something new. It's just like, wait, that's how it works? And you're like, yeah, that's how it works. So yeah. I don't have anything else to say about this pump air shooter. Like, it's It's good. I don't know if it's the best. Okay, well, again, let's just put it in relative terms. Is it better than the fan shooter? Maybe. The only problem with the fan shooter is, like, if you could figure out how to place the ball at the right time, then it's not an issue. Some said 6, but that might be for the whole thing. Yeah, 6 motors is a lot, to be honest. Yeah. Yeah, because some of these robotic arms, as much as I know, is that there's various degrees of freedom. So there's like, well, there's 6 degrees of freedom, right? So there's translation, so X, Y, Z. You can just move in those space. And then there's rotation, so rotation across around each axis. So if it's like if it's a full-on mobile robotic arm, maybe has the ability to do that. So maybe that's why they need 6 motors. Maybe that's what I'm thinking. So, but that's a pretty crazy robotic arm, if you think about it. That thing could just move fluidly, like in space. Like that's pretty crazy. Okay, so relatively speaking, it's on par at least with the fan shooter. I'll give it that. Is it better than a catapult? The catapult is more difficult design simply because we gotta take into account of the length of the arm. Like, we gotta know how long the arm is, or how far away the ball is from the rotation or the axis of rotation, because that determines the speed of the ball or the linear velocity of the ball. So it takes in more, like, we have to worry about a little bit more things. It's more technical, but it doesn't make it a worse design, though. It's just more technical. But that does require knowing where the ball is on the arm. So, oh yes, Stan. There I am streaming to 2 streams right now, on Twitch and on YouTube. So, no one else has commented yet. I'm just talking out loud. You know, I'm trying to keep the video going. So, I'll try my best to read the comments out loud so everyone gets the same comments. So everyone's in the same boat. Sorry about that if that's confusing. So, besides that, it's more technical. Doesn't mean it's a bad design, but it's just more technical. That's all I could say about that. Okay, Dan. Now, it doesn't matter what platform you watch on. Everyone gets to see it. So, yeah, it's fine if you go on Twitch or YouTube. Let's see. So, 6, 5. It's like a 5.5. I think it's a 5.5. Simply because, yeah, you're in 2 places at once. What is that, like quantum state entanglement or something? I don't know. I'm a nerd when it comes to that. All right, here we go. So, we got a catapult fan shooter, pump air shooter. I would say that it's a 5.5. I don't know. Maybe I'm the reason why I say it. Let me just say it, because I need to validate my reasoning. I try my best to validate my reasoning. I'm just not trying to just say words without, giving them weight. So, the reason why I say it's on par is because although the pump air shooter solves the problem of not having a ball, the ball being at a specific location at a certain time, it does have the con of air leaking, which is basically the drawback of how the ball's gonna be placed in the fan shooter, if that makes sense. So, What that means is, I think, you basically get a con and a pro, which just basically negates each other. Therefore, it's on the same scale or rating. I don't know. I think so. I'm gonna give it 5.5. It's good. It's not that much different than the fan shooter. So, 5.5. This is the worst drawing I've done so far. 5.5. I can't draw today. Here we go. So, there's that. Okay, 5.5. Now let's go to the gravity shooter. This one's a very simple design, to be honest. Well, simple in concept, not necessarily design. Because we're simply just using gravity and like an elevator. So we have a ball, we're lifting the ball up from the ground state all the way up to one of these potential levels. We have one level here, 2, 3, and so on over there, and then we push the ball off, and then it rolls down this ramp and then launches the ball. Very simple in concept. In execution, I'm not sure. I'm pretty sure we could build something like this. The only drawback that I see almost immediately is that we have a discrete, I guess it's not a drawback, but a design potential issue is that it's a discrete system. So what that means is that although the ball can go up to any state, you don't have that much control on how far you can launch the ball. Like, it's either 1, 2, 3, or 4. There's no in between. There's no 3.5, 2.5, and so on. So if someone wants to launch the ball very precisely, like maybe what if we place the cup in a position, so like let's say we have a table, right? This is a cup, and then here's another cup. What if we say, if we launch the ball, right, and we, I don't know, from state 2, we launch the ball and it happens to land right here, and then we launch the ball again, and what if we land right here? Since those positions are technically, in theory, locked in place, the user can't go in between 2 and 3 because their power levels are dependent on the predefined system that doesn't change. So if the game happens to place a cup, which is likely, in a spot that this mechanism can't launch at, then we can't do anything about that. So it's almost like the user is stuck in limbo because they can't accurately get the ball to hit the cup. That's pretty major, because now we gotta be worried about the cups, the position of the cups or the position of the robot, like the physical position. So that is definitely an issue, I think. Now it might be negligible, but it is still a possibility. So there's that. That affects the game tremendously. And I feel like, I don't know, I feel like that's pretty big. What else? What else can go wrong, or what can go right? It's gonna be huge. I think this thing is gonna be big. This is a fairly large system. So, I don't know, like if we do some quick math to figure out how high this would get. Oh, well, I guess this depends on the angle, really. It's not based on, well, it is based on how high it is, but if we get, okay, no, actually the angle should be 45, and I'll tell you guys why. The angle should be 45 degrees, simply because if you do the math and all the analysis, 45 degrees will launch the ball and such that it's the farthest distance that the ball can go. So we would have to make sure, I mean, if we want to really optimize the efficiency of this ramp, we want to launch the ball at 45 degrees. Again, because that's the maximum distance that the ball can be traveled or be launched at, given the system. So we would want to give that 45 degrees. Besides that, then if we're given that, I don't know, we could do some quick math, I guess. If we have some potential, right? Let's say this is our ramp. Here's some actual engineering, some R&D, some some of the boring stuff, some may say. But this is the height, right? So this is the height of the ball, and then it's gonna gain some velocity sometime later with an angle of 45 degrees. So by knowing that, we can determine we could determine that if we have initial potential energy goes into kinetic energy, what we could say is that mgh is equal to the final potential or kinetic energy, which is 1/2 mv squared, right? So we could find the ball to be square root 2gh. So that's the magnitude of the velocity when it leaves the ramp, essentially. So from there, we know how essentially that the farthest distance is dependent on the horizontal velocity of the ball. So if we take, wow, I didn't know it was gonna go that detailed, but this is actually a pretty classical problem. Like if you're going to study physics or you're studying physics now, you would definitely see something like this. So so again, this is the ramp, so we're launching it. So the horizontal velocity, Vx, right? I haven't done stuff like this for a while, so it's kind of a nice refresher. The magnitude, which is 2gh, the cosine of theta. So this will determine how far we could launch the ball in theory, right? If we're given the speed, what else do we need to know? So that's the initial velocity in the horizontal direction. Oh, this is going to be more detailed than I thought. I really don't want to do all the math because I don't want to bore you guys. But essentially, this is the horizontal velocity. So once we get the horizontal velocity, we can determine the distance. So distance will be velocity times time. Yeah. So time traveled, but we don't have to have this time dependent because we know that when the ball's launched, it's going to come back to the same location in theory. So this will be the maximum distance, if that makes sense, from here to here. So that'll be like d. So we could use that to determine how far we could launch the ball. Maybe we're overshooting it, to be honest. We're in control of that. We're in control of h, so we could control that completely. But basically, we could vary this height, determine what are our actual bounds. I mean, this is getting too detailed because I don't want to go too detailed because we didn't choose this mechanism to design it. But this can tell us whether or not we're going to hit the cup or not. Maybe we're going to overshoot the cup. Maybe our ramp is going to be too small. Like maybe practicality comes into play and the ball doesn't even, or we make this ramp too long, and then so there's a whole lot of different criteria when it comes to this, but I don't want to go too deep into that unless we choose this design. But the point is, I kind of strayed off the whole conversation, is that if we have a discrete system, we want to make sure that it is still able to hit every cup on the table. If it doesn't, that's a major issue. So I believe that is a big con. That's what that brief tangent was. So Con. This is a con. Uh, might I don't know. I'm gonna call it limbo because if the player can't hit this cup ever because of based on our design, then they're in limbo. They can't really progress anymore, so they're stuck there. So I feel like that's probably the biggest flaw out of like all of them, in my opinion. Because all these seem analog or they're variable. Um, the spring-loaded shooter, if we change it to a piston, I still have to think about that. I research more about whether or not we can make it variable. But yeah, every other design has the ability to be fine-tuned or be a precise number if need be. Okay. So maybe not the best design. Pretty cool in concept. Pretty classical. Pretty old school. But yeah. It also, again, it's gonna be big. I feel like that's a drawback. Like if you can't put this on a table or you can't put this on a stand so that it's level with the table, then that's an issue, right? What are you gonna do? You're not gonna launch this from the floor. I mean, I guess you can, but it's just it's I think it's more inconvenient in terms of space and stuff like that. So it's also big. So this I'm sorry if this thing's very cluttered. I should draw lines to mark off where it is. So here, let me do this. So it helps me, you, and everyone else to see this better. So this is like that, and then this one kind of goes around like that. This one goes like that. I don't want to cover it. Like that, and then something like that. There. Or there. Okay. I'm just gonna close this off. Screw it. Okay. Oh, that probably made it worse, to be honest. That just made it more busy. Jesus. Okay. So besides that, okay, now let's start rating this in relative terms, because again, you need to have a basis for everything before you start choosing stuff. So what we're gonna do is rate it off the other designs and see if what they're comparable to, what they are, what they can do compared to other systems. Okay, so this one, I think based off all the other designs, it is a discrete system. It can be a bad thing, but it could also be sufficient for our needs. So I think that's a big drawback there, and I think that's why it brings this one down below all the others. It's also big. I don't want it to be too big. You can also think about like how we're gonna make the ramp. I'm not that technically skilled with my hands that well. I mean, I could try to make a ramp out of wood. I don't know. I don't even know how to even start that. Like, how do you bend wood? That's a weird question. How do you? I don't know. How do you make a curve? I guess. I mean, maybe plywood. Maybe you could do it with plywood. But like, that's pretty big. I don't know. I'm thinking out loud. I'm not the most practical at sometimes when it comes to building, but if you guys have better ways of doing that, then let me know. We also need to somehow push the ball off the elevator. Is it too big? And yeah, I don't know. What else can we do? Yeah, I don't know. I think that's it. I mean, I want to give it like a 4 or a 3.5. I don't know, maybe it's on par with the spring-loaded shooter, the original design at least. If we change it to a piston, that may move it up. But as far as I know, it's probably like a 4. So I'm gonna give it a 4. If you feel like it shouldn't be a 4, let me know. But I feel like it's a 4. I think a solid 4 should be good for now. 4 out of 10. This is very cluttered. I'm very sorry for that, but it shows how like the mind just wanders and just does its thing. Ideas just come to fruition on its own. So let's see. So yeah, 4 out of 10. Okay. So before we, I mean, based off this chart, what it's telling me, or not chart, but based off this diagram, it's telling me that this is our best design. I circled like 3 of them. This is gonna be our best design. The tennis ball shooter, and I kind of agree with it. If you guys think otherwise, let me know. But I think the shooting mechanism for that is not bad. The spring-loaded shooter, I want to research more. I think that's what we're gonna do next. I think I want to research that the variable solenoid. I think that's a great contender. The catapult comes up close. So does the fan shooter. I guess they're all pretty close, but yeah, I think I think what I want to do. I feel like this is what I want to do. Is hey man, hey Dane, yeah, don't worry about it. I'm talking to myself anyway. It's all good. I'm just thinking out loud. I'm just if you guys need it, if you guys want to chime in, let me know. Just type in the chat whatever you guys want to say. But what I'm trying to figure out is I lost my train of thought. What I want to figure out first is before we start choosing one, although it looks like the tennis ball shooter might be the winner, what I want to do is look up how a solenoid works, at least electronically. If we could vary the speed of the solenoid, that may be a good idea, because that is a very efficient design. Simply because all we have to do is control a piston. If we can control the piston, then all we have to do is put a tube at the end of it. It's pretty much as simple as the fan shooter. And if we put the spring-loaded clip with this thing, it's practically it's pretty versatile. So that's why I want to stick with the spring-loaded shooter. Okay, let's do some research. Hopefully, you guys don't mind that. Do some research, see if we could find some variable solenoids. If so, I believe we'll move this up to an 8. I don't know. That sounds a little crazy, I know, but I might move it up to an 8 because it's just like, why not? It's very simple. Okay, so let's look up that. Let me see if I can get this set up. And if you guys want to redesign or do something different, or if you guys have another idea how to do something, let me know. But as far as what we're going to do now is just look up how to, or if we could find a solenoid. So let me set this up. How do we do this? Show. Alright, here we go. So, is there such a thing as a variable solenoid? And can we control it? I feel like it is. I mean, why wouldn't there be? Arduino. Let's do Arduino. Because usually that's... Let's see our specs. Ooh, mouser. my company that I work for, we use this as a approved supplier, and I look at this. I go on this website quite frequently because we gotta find parts. So, pretty familiar with this website. Not that I'm proud of it, but I guess this is what I do on the daily basis, so to speak. I look at parts. um, Besides that, let's see. Can we vary this? That's the main thing. We have a manufacturing. Do we have a spec sheet? There's no spec sheet. Usually it's right here. What if we do this? So 412 out of 3. Here we go. Oh, DigiKey as well. Yeah, classics. Where's the? Okay, we got a drawing. Ooh, okay, but it doesn't tell me. I'm assuming Chinese. It's 24 volt, which may be an issue. Is it DC? That's DC 24 volt, but can we vary it? Let's see how to vary a solenoid. There's solenoid actuary theory. Let's see. Solenoid and the basic electrical. Yes. In and out. Yes. So solenoid moves in and out to control the piston. Restores its original state by using a spring. Yes. Both type of. Both types of solenoids, linear and rotational, are available as either a holding, continuously energized, or a latching type, on-off pulse, with the latching types being used in either energized or powered off locations. Not what I'm looking for. Okay, right here. Linear solenoids can be also designed for proportional motion control, where the plunger position is proportional to the power input. That is exactly what we need. When the electric current flows through the conductor, it generates a magnetic field. Yes, that's how you control it. Okay. If you guys don't know, a solenoid is how it works is essentially there's a wire, a copper wire, or some sort of wire like that, and it's wrapped around, usually around a magnet, and then a magnetic field is created by passing current through the wire. And that's essentially what it's showing here. So by basically increasing the magnetic field, or the magnitude of the magnetic field, we can control basically the little piston that goes in between it. So we can push it out or at a speed that we want proportional to the current that's going into the wire. So that's what we could do. Or that's what a solenoid does. So when an electric current pass behaves like a plunger, yeah. So here we go. Pole type, rotary, no. Solenoid switching, transistor, solenoid duty cycle. Okay, that's exactly this one. With a few all or nothing solenoids, and some of them are more variable. Half power equals half open, 1/3 power equals quarter open. Which would be easiest to do measuring the current drawn, or to do so. Says 1/4 would be opening the solenoid. So it looks like we can. which is a good thing because if we can vary the solenoid or the speed of the solenoid, which is controlling the force that is put onto the ping pong ball, we can then just launch the ping pong ball using just a piston. So I think we could just do that. So let me type in force just to make sure. Variable force solenoid. Yes, spring force. Okay, well, yeah. Okay, I mean, it seems to be fine to do that. I just need to find that solenoid. Using a solenoid for variable force. A horn-like device with a variable pitch. Oh, okay. So yeah, this is kind of what we're doing. This guy is designing a horn with a variable pitch, and he's varying the pitch by pressing the horn. So half press means like a different pitch, and then full press is probably a higher pitch. Yeah, the function of the solenoid would not. In the U.S., electrically driven train horns consist of tuned horns, each had different frequency. I know that could. Yeah, we'll also need a flyback diode as well, because again, we need to worry about protecting our circuit as well, because what can happen with the solenoid or even a DC motor is that when it's spinning or getting powered, I guess, it can induce a magnetic field, and that magnetic field stores energy in terms of current. So once you basically store that magnetic field or get it going, essentially once you cut it off, the current could draw back into the circuit and potentially damage it because it's a high fluctuation of current, if that makes sense. It's kind of hard to explain, but essentially there's back current, if you want to say that, and which can damage our electronics. But we basically put a diode there, and that can basically save us. Or it's called a flyback diode or a Shakti diode, I believe that's what it's called. Those are basically a higher rated diode to prevent it from basically getting damaged. Like that diode is specifically made for that purpose. So we could do that. We're gonna have to do that. Their question, but it could be fine for you if you aren't. Continuous operations? Let's see that. I don't know what that is. Continuous operations. Yeah, I think that's what we need. Continuous duty solenoid. That sounds about right. Oh, damn. Alright. Yes, what is a continuous duty solenoid? I don't know what this is. So solenoids are valves or metal coin. Okay, these devices are designed to convert electrical energy to mechanical power. Continuous duty solenoids are rated for 100% duty cycle. Okay. Solenoids are rated for how much time they can be powered on. Sorry if this was too small. Continuous duty solenoids are designed for operating conditions which they are subjected to heavy use. Consequently, they are rated to be used in 100% duty cycles or constant use. Oh. Sorry about that. Okay. So, yeah, maybe this is not what we need. The solenoid seems like something else. I just need a variable solenoid. There has to be one. I feel like there has to be one. I don't see why not. Oh, we were just here. Let's see. Let us see. So solenoids, culture. Oh, come on. So, how else do you type this? Solenoid, vary force. Force. Oh, here we go. Force solenoid? Is that what we need? I mean, it sounds too obvious. Let's see. How much force solenoid had force from? Let's see. Make master car. Let's see if these guys would have it. So, hopefully, if we type in solenoid, I feel like we can. They called it, we need compact linear solenoids. Yeah, we need one of these. So, let's see. It's such a small range though. That's what I'm worried about. Like, we only have 0.4 inches to work with, and I feel like that's an issue. Force at 100% stroke. 7 ounces. We don't need for DC voltage pull push. We just need push. We don't need pull. Well, I guess it doesn't matter. 45 ounces. That's pretty good. Let's see. So 45 ounces of push. So the question is not to figure out how much force we need, but like how can we vary it? That's like all I need to know. Like if I were to put, let's see, so we have 12 volts DC. So if it's 45 ounces or roughly 3 or 4 pounds of force pushed onto the ping pong ball, I need to know if, let's say, if I put 6 volts in, will I get, a pound of force? It seems obvious, to be honest, that it does, but I just want to make sure. How do you wire this as well? I mean, it's probably pretty obvious, but you just connect 12 volts to it, I'm assuming. I'm assuming these are the positive and negative leads. So it's a 1/4-20 thread. We don't need... Does it give you a spec sheet? I guess this is a spec sheet. Does it come with a wire? What if I did this? What else is important? The diameter? Yeah, it's fine. We just need to make sure, I guess another important thing when it comes to launching the ball if we use a solenoid is to make sure that the piston lines up directly in the middle of the ping pong ball. It shouldn't be a problem. In theory, it shouldn't be a problem, but it might be. It's also dependent on the tube that we choose. So, you have to think about that. But besides that, I feel like it's $162. I don't know about that one. That is a no-go. Okay, let's try something else. I didn't think they were gonna be that expensive. What if okay, let's say 12 volt or 6 volt DC. No, 12 volt DC. Oh, we don't need sealed. We need push. I guess sealed ones are not that bad. force at 50% stroke. 70 ounces. I think 1 ounce of force. It's so weak. Why? Ideally, I want like this one or this one. 25 ounces. That's about I guess a pound is a lot. Like if you think about it. Okay. Here's some analysis. Okay, it's a momentum balance, meaning that if we look at this, we have, depending how fast it pushes, that'll determine how large. Well, I guess it doesn't matter. Well, it does matter because the ping pong ball is very light, so it is a momentum balance regardless. But what makes it? Well, no, you get. I'm stuck. Never mind. I thought I was going somewhere, but I'm not. It just worries me that I'm not gonna be able to control it. That's like the only issue that I have. How are we gonna mount this thing? I don't know how to mount this thing. It looks like it's just a cylinder. This one actually comes with wires, and like I think it was a 1/4 screw, so we can actually screw this in and then feed the wires somewhere so it doesn't get in the way. I like that, but these things are expensive, like stupid expensive. I'm gonna type in Arduino. Arduino solenoid, and it's probably like this one. I don't like. What's wrong with this? Does it have enough force to give us something? Because like if we could find a solenoid that does exactly what we need to, this project would be like pretty straightforward. Continue. Okay, wait. The C frame. 500 VRMS. Oh, here we go. I missed it. Okay. Let's see. Oh, here we go. Force gross without spring. Okay, so this is out being pushed back. That's what this graph is showing. So, what do we have? Well, this is a pull. Oh, we want push. Do we have push? Oh, we don't. Great. Okay. So here we go. 100% duty cycle, 3 watts. So we're getting around half a pound of force. That's probably fine. I can't put that in perspective. Like if you throw a ping pong ball, how much force are you giving it? Not much, probably. So if we give this 10% duty cycle, we get... Oh, now I get it now. I think I get why there's an inverse relationship between the percentage of the duty cycle to the power. Because I think this is the problem what I had last string. Was like, I saw this before. I was like, why is that happening? But I think it makes sense. What it's saying is that if we put 100% duty cycle into the solenoid, what a duty cycle is essentially that it's a frequency or a wave of on and off. So it looks like a square wave. Let me show you a square wave. This is my thought process. Maybe I'm completely wrong about this, but it seems like it makes sense. So this right here is called a square wave. It's pretty self-explanatory. Basically, we have a -1 state or an off state, and then we have a +1 state, being an on state. And then the duty cycle is basically how frequently is it on. So when you have 100% duty cycle, what it is going to be a straight line, basically a straight line at 1, meaning it's always on. So let's see if I could maybe show you guys that 100% duty cycle. If it shows up in Google, I think I am right. Here we go. Yeah, so this is probably a better image. So yeah, so this is our on and off state. So 100% means it's always on. 80% means it's on 80% of the time. 50%, 50% of the time, and 20%, 20% of the time, 0% of the time, so forth. So the reason why I think there's an inverse relationship between the solenoid's duty cycle to the power input is that if you have the solenoid always on, it doesn't allow enough time for the magnetic field to build up in the solenoid. Therefore, you get less force. So that's why we get a low force, which is red. So if you have a 100% duty cycle, it's saying that we put 3 watts in because it's not a lot of energy to launch the solenoid because it doesn't have enough time to recharge or rebuild that magnetic field. And then therefore we're getting a low power input or output, I should say. So if we have 50%, it means it's 50% on and then 50% off. And during that time of being off, I'm assuming, correct me if I'm wrong, and if anyone knows this, that being off allows the magnetic field to build up, therefore giving it more energy to be launched for at a higher speed or whatever. And then, so that's why I think there's an inverse relationship. Therefore, if you have a 10% duty cycle, we should be able to create 5.34 pounds of force, I think. So given that means we can vary this thing. And if we could get 5.34 pounds out of this thing, this is pretty good. Dan, you're crazy. I'll give you that. Yeah, I remember staying up late, and I remember this is a while ago. By the way, if you guys are listening, Dane, he's a frequent member in the chat. He's pretty much up late. I'm guessing somewhere outside the U.S. I'm not sure, but he's basically up late watching the stream, which I really appreciate. Dedicated fan, I really appreciate that. But he's out late, and it's already becoming light outside. So I remember this one time. It was like a while ago, back in like when I was like a kid. I slept over at a friend's house, and it was like one of the like first couple times I slept over at a friend's house, and I remember we just stood up all night just playing video games. Like we did not care. Like it was like one of the funnest times, you know. Yeah, those were the days. Just playing video games all night. Yeah. 3:33. Damn, that is pretty early. I tell you that much. That is pretty early in the morning. Anyway, getting sidetracked a little bit. So yeah, I think we're fine. I need to see how this thing works though. It's high speed. It's small. It's lightweight. And that means we could put this thing on like something that can move and rotate probably pretty easily. Does it give us the weight? Plunger weight, total weight. About not even an ounce? Not even an ounce? It seems so light. Huh. Okay. It's kind of... How small is this thing then? Wait, they had a diagram. I'm assuming that's in inches and bold. So, and then this is millimeters. Yeah. Wait, so how does this thing work? So, okay. If you guys never seen an engineering drawing before, this is called an engineering drawing. It's very, very loose. This is more consumer friendly than anything. But how they display these different views is two-dimensionally, right? Because we give a piece of paper to someone and we tell them how to build it, or at least give them some idea of how it should look like. It's very useful if you're trying to, if you buy parts or something and you need to inspect the part before you actually start using the part. Because if you don't inspect the part, then you don't know if you got the right part, or maybe they did something wrong, or maybe the part is not right. It's basic inspection. So this is how they usually show how to fully define an object without using words, essentially, or using minimal amount of words. So this is this is a third angle projection, I believe, meaning this is a very custom, or not pretty common way of how engineering drawings are done in the US. Meaning this is the front view, this is the front of the device, and then they have the right view, which is the right side of the device. Then in the left view, this is the left side of the device, and then the bottom view, this is the bottom view of the device, and then if they had a top view, it would be up here, which would be the top view of the device. Technically, you only need 3 planes. Depending on how complex the part is, you only need 3 planes to fully define the part. Here they did 4, simply because if you did, because there was holes on the bottom side, and you don't really see it here. You see it with the dash lines. There's also this hole on this side, or not hole. This arm, or this piston. Oh, you're from Britain. Well, that's pretty cool, actually. How's it going over there? I feel like, I don't know. I really don't know what's going on too much over there, but that's pretty cool. It is pretty cool. Huh. Yeah, it kind of blows my mind that people who watch my channel or even my streams are like around the world. And, I mean, most of them, like a large majority of them are from the U.S. But yeah, it's pretty cool to see that people around the world are watching. So it's really cool, really cool. So yeah. What I'm worried about is like this hole right here. Like, why is there a hole here? Can we miniature size? Yes. Ooh, yeah. Yeah, to be honest, over here is kind of crazy. I live in California, and the coronavirus has been pretty gnarly. They're actually opening stuff back up, which is kind of mind-boggling. I'm just like, I feel like it's quick, a little too quick. But I mean, if people are willing to go out, I mean, I guess, do you. And then we also have those protests going on, which is another issue. But yeah, it's pretty crazy. And the combination with the virus is not really a good thing, at least in terms of spreading the virus, if that makes sense. Like, yeah. So I don't know. I think we're moving a little fast, but I guess people in California are ready to get back to the normal way of things. Yeah. So yeah, it's pretty crazy. But hopefully it gets better over there in Britain, like for everywhere, to be honest. But yeah, it's crazy. Crazy stuff going on in the world this year. Okay. Back to the design. Okay. If we choose this, I think we'll be fine. And it's cheap. And we can control it. So I just want to understand why they put a little pin here. Like, what do we attach there? I guess we could attach anything we want, really. It doesn't really matter. But that's so weird. Can we get a YouTube video of this thing? I just want to see it operating. I'm just interested. So I guess not. Solenoid, come on. They don't have it. Okay. I feel like we can go with this design. You may have to look more into these different types of solenoids, but I think that is the best design. How about this one? I think we were looking at this actually, but they didn't give us a spec sheet. That's what I'm trying to figure out. Like, if we could figure out the solenoid thing, I think we have our design. What was it? 412? I think it was 412. They don't have it. Oh wait, was that it? Oh yeah, they're down here. Yeah, this thing. Can you just give me... They don't have the spec sheet, which is bothering me. I need the spec sheet. But, yeah, cases here are at an all-time high, but the government here are like 4-year-olds and easing up on the lockdown. Yeah, man. Just, just, just stay inside, or I mean, do whatever you want to do, but like, yeah, just try your best to stay away from, um, people, or stay at a distance at least, or try your best to just distance yourself. I mean, that's the only way to go about it. Um, but you know, but also, I mean, to be honest, like, I'm kind of an introvert, so not too much has changed. You know what I mean? Like, it's like, oh, the virus is here. Like, oh, wow. I mean, it did affect my life a little bit, but it's just like not much has really changed besides like the slight annoyances of things, like you can't find any stuff in stores, or some restaurants you can't eat out at restaurants, or stuff like that. It's just a slight annoyance. Maybe I'm a little too privileged when it comes to that, but uh, you know, yeah, it's just, yeah, I'm not really. I don't really mind staying in too much. I mean, I do like going out, at least hanging out with friends and seeing them once in a while. But like, other than that, it's just like, you just hop on the Discord or something and just play some video games. Nothing too much. Um, what else? 7:42. We have another hour before the stream is up. So there's a few people in here. Just letting you guys know, I do stream Monday, Wednesday, or I changed the stream schedule because I want to take 2 days off on the week streaming, simply because I want to work on my YouTube stuff, like actual YouTube content. And I have a really good idea. I think you guys will enjoy it coming up. I'm still working on it, but I think it'll be pretty fun to do. Hopefully, you guys will like it. Um, it's more on the entertaining side of things, nothing too technical like this stream. So hopefully you guys will like it. But see, when I see this, I know this is not the solenoid we're working with, but what I see here is Boolean logic. Maybe if I could zoom in. I see Boolean logic, meaning high or low, or on off, or 0 and 1. I see Boolean logic, which gives me the idea that it's not variable, which is what I want to avoid. You must go into the shops for sweets, but otherwise not different. What's your favorite sweet? Or candy? We call it candy over here. Yeah. Well, I hope your Chromebook gets working. Or wait, no, I hope your phone gets working. Sucks to not have a phone for a bit. But yeah, back to this. If we have a high and low input as the only option for the solenoid, that means it's discrete signal or discrete output, which is not necessarily a good thing. Essentially, what? I mean, I don't know. Connect your solenoid to separate lines on your breadboard, 1 to 5 power and the other. Yeah, connect your diode between the connect blah blah blah. Huh. See, that's what I don't want. I don't want this. Well, I guess I do want that, but I want to change the speed. I feel like it's not going to be a good design because I think the speed is highly dependent on how long the piston is. Right? I mean, no, I guess not. It doesn't matter how long the piston is. Oh, I guess it does in this. I don't know. I'm losing my train of thought again. What else can we do? See, but the one we saw seemed like you could vary it though. Frame pull continuous. This one's a pull. You want to push. That's the key thing about this. We need to make sure this thing pushes, not pulls. Okay, let's try it. Let's see if this solves our problem. So yes. Can he vary the speed? See, he has Boolean logic too, which I don't want. Okay. So that's like the duty cycle. Huh. Okay, I got angry and threw it at the wall. I don't know what moams are. I don't know if I'm even pronouncing that right, correctly. To be honest, moams. I'm kind of curious. Is it like a chocolate or something? It sounds like a chocolate. Oh no, it's a. Oh, these are like Oh no, someone's awake. You better watch out. Okay, yeah, this looks like nerds. Oh no, these are like starbursts. I don't know what these are, to be honest. Like Laffy Taffy almost. Yeah, I don't know. I'm from America, so I don't know what those things are. Anyway, we're getting sidetracked. I need a variable solenoid. Does anyone know if there's such a thing as a variable solenoid? I don't know of one, to be honest. I feel like varying the force of a solenoid. The reason why we're searching this so hard is because this might be the potential design that we choose. More like Starburst. Okay, yeah. That's what I thought. It looks like Starburst, to be honest. Varying the force of a solenoid. Or do we know? Maybe. For variable force. This is... I think we looked at this before. Yeah, we did. Controlling a solenoid. We looked at this too. Yeah, I don't know if we can control it. I want to avoid the on-off state. Yeah, I'm not sure if we can anymore. I was pretty confident at first, but now I just don't think you can. We have them here. Oh, you guys do have Starburst over there? That's pretty cool. I mean, whether... I guess we have stores that have other, like, foreign candy as well, but I'm not sure what foreign candy. Or sweets, if you excuse my language. I'm joking. Okay, yeah, I'm not sure. Oh, that's the opposite end of it. Oh, I'm stupid. Okay, so this goes on the opposite end. This what prevents the piston from going all the way through. I just need to make it to 5 a.m. You're crazy. You got like 2.5 hours or something like that, or an hour and a half. Maybe just go to Reddit. Reddit's usually the right answer. This one? A spring? See right here. You see this right here? This is what is stopping us from using a solenoid. Right here. Which is why they're good as an on-off control. That's exactly what we don't want. So this guy has a design solution. Compressor, large air storage tank, electronic air regulator, air storage tank with a pressure sensor going to a T-joint. Each side of the T-joint goes the solenoid valve to the piston, solenoid valve to the ambient. Okay, so maybe we can't use a solenoid. If that's the case, then I guess we're fine. I guess we have our design. Which ones we'll choose? Okay, that's fine. Yeah, wait. I need proportional solenoid. This is what I need, I think. Proportional solenoids and proportional solenoid valves are often used in applications requiring variable and precise control. Yes, by controlling an electric control signal into proportional mechanical force, proportional solenoids are able to achieve varying position or force. During operation, spring force balances solenoid force to position the armature in a position to the input signal. As current is applied, the force of the armature against the force of the spring holds the solenoid in a set position until the applied current is met. Okay. Let's find one of those. Proportional solenoid. Let's type in Reddit again, just in case. Oh, perfect. Ask engineers. Here we go. Proportional valve or electrically actuated valve depending on application. Basically, I need a solenoid valve that opens proportional to an input I give it, such as 50% open when I feed 12 volts to a 24 volt solenoid. Does such thing exist? Do I need other options? I've never really looked. Yeah, I feel like the same person. Continue this thread. Most proportional valves I have seen are current controlled PWM, so you may have better luck searching for those. These guys go up to 6 inches or more. Okay, they're not there anymore. I've yet to see one. As soon as I will get a chance, I usually use diluted control valve for this sort of application. So, if this tells us that we could proportionally control this valve, we could use it. But I need to figure out where we could get one. Let's see what this says. That's not what we need. Oh, I don't need a solenoid valve. I need a solenoid actuator. I guess they're the same thing, huh? How about this one? This one looks right. So that means I need to get something that goes on the end of this, because the piston will just shoot out of this. This is 24 volts DC. Can we get one 12 volts? So this is a... Okay, here we go. Don't let her find you. Or just pretend you're asleep. Do the classic like Scooby-Doo trick and put like a pillow underneath the blanket and say you're asleep. And then pop outside the other door in the hallway like some other, again, Scooby-Doo trick. I'm stupid, by the way, don't listen to me. Here we go. 12 volts. Current, blah, blah, blah. Typical pull force stroke. Continuous intermittent duty cycle. We want push, though. We don't want pull. Why is it only giving us pull? I want push. I don't want pull. Here we go. Here we go. This one? This one's push pull. Let's see. What is this? This is not even like what I looked up. I can't find anything. If you guys, well, no. Let me see. Do you? How about this one? Does this give us a spec sheet? A useful one? Oh no. This looks more complicated. Here we go. So maximum duty cycle 10 whatever. Watts, blah blah blah. Volts DC, nominal. Okay. Typical force at 20 degrees C. Well, this is very, well, no, they're all 20. Okay, so this one is, what makes this different? Are these the, oh, they're different sizes. Okay, so that's what's different. Wait, no. Oh, this is speed. Typical speed. And this is force. Typical force. Okay. Pounds, 20 pounds. That's more than enough. I don't think we need to vary that much in terms of forces. Like 10 or so pounds. That's a lot. But I'm still trying to figure out if we could actually vary this. Hey Dane, no, don't worry. If you need to leave early, it's fine. Again, if you need to catch the stream or if you want to watch the stream, it will be archived and it should be up by tomorrow. It usually takes time to process, so if you need to go, it's fine. Hopefully you catch the next one. It's cool. You don't have to stay here. Just letting you know. Okay. So can we vary them? That's all I need to know. Let me just look up a proportional solenoid. Actually, I'll probably solve all the issues. Solenoid fundamentals, proportional hydraulics, proportional valve. This one? Is he gonna power it? Tell me if he's... Oh, this is like it's a valve, not a piston. The next stream is tomorrow, ideally. So tomorrow around the same time. It's mostly because I get off of work, I I need to eat, and then I basically hop onto the stream, and then that's pretty much how it goes. Yeah, this is not the most exciting stuff for this stream. I know that, but I just really need to know how we're gonna vary the solenoid. Because if we could vary the solenoid, this design is super simple, and that's why I'm spending more time on this. Proportional. I'm lost for words now. Proportional solenoid. See, this one's pull as well. Oh, maybe that's how you distinguish between pull and push. I didn't think about that. So, I think I get why there's like a hole here. Essentially, you could attach the thing you want to pull. Makes sense, right? For pushing it, you don't need to attach something. Well, I guess you do. But in theory, I think that's why we have this hole here. So you could attach something, and so if you want to pull it, you could just put it on that. Makes sense. Okay. So that's how we could distinguish between push and pull. Solenoids, at least. So the more I look at it, the more I start understanding the madness. Well, I don't want flow adjustment. I want piston adjustment, if possible. Proportional piston solenoid. This one. Duty cycle intermittent. Specifications. Coil voltages 6, 12, 24, 115. Wire leads 24 gauge. Alright, Dane, no worries. If you need to go, I'll see you next time. I'll see you tomorrow, Wednesday, or next week, whenever you get a chance. Thank you for dropping by if you need to go. Yeah, no worries. No worries. I'll be here. What? I'm still looking for this proportional valve or solenoid. I can't find one though. I legitimately can't find one. Alright, see you, Dane. Sleep tight. Okay, this one? I don't know if we'll ever find one. No. Continuous duty, what is that? Yep. Let me see this. So here we go. We have a high performance blah 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 blah. Coiled 100% continuous, 25% intermittent, 10% intermittent, 1% pulse. Huh. I don't know what. I'm just trying to operate one at a variable. Okay, I have way too many tabs open. I'm gonna give this a few more minutes before I just say we can't do it. So again, we're trying to find a valve, a solenoid valve, to vary, because we can use a valve to be binary, I mean on and off, but we need to vary it so we can control the speed of the ball or how far the ball goes. So we need to know, we need to be able to control it variably. which is pretty important. So yeah, we're getting proportional valves, but not pistons, which is what we need. Jesus. Okay. See, this one looks like a valve. Yeah, so I don't. Maybe we can't control it. I'm assuming we're not going to be able to control it. Okay. Well, that was a good 30 minutes or so seeing if we can control it or not. So I'm assuming we can't. I'm just gonna assume we can't, which is unfortunate because that would have been a great design. So let me move this a little bit. There we go. Yeah. So excuse the clutteredness. It just shows how my brain works or how our brains work. It's just ideas coming to life. But what we were doing originally, we rated all of these to choose our design. Just a quick recap. We got a shooting mechanism that we're trying to figure out. We rated them. We gave 7, 4, 5.5, 6s, 5.5s, 4s to each one of these designs. And it seems like our winner so far is going to be this ping pong ball, tennis ball shooter. Its design, at least. I really wanted this one to win because I was trying to find a solenoid to go in place of this spring, because that's a way simpler design. Let me see if I could. It's a way simpler in design. So, and I believe if we were to find a proportional solenoid that we could vary the speed or whatever so we could control how far the ball goes, I believe this would have been the winning design. But since I don't think we can, it's not that great. It's actually not great. Or not the best. So I think what we're gonna do is just stick with this one. We're gonna stick with the shooting mechanism that is the tennis ball shooter. So, if you guys forgot how this thing works, let me briefly explain it. Essentially, we have, this is gonna be a tube. So we're gonna put a tube right here, probably some PVC pipe or something like that, and then we're gonna basically drive the ball by using two wheels spinning at a certain velocity or RPM. And then how that equates to the ball being launched is that the ball is going to touch those two wheels, and then based on the speed of the two wheels, it'll give the ball some velocity, which then launches the ball. That's essentially how it's going to go down, right? So if you want to see an example of this, I don't think it's too surprising. A tennis ball launcher. This is why we called it a tennis ball launcher device or mechanism. So I remember. Oh, this is it. You saw this video before. No, he actually did a 3D model of it. So yeah, so essentially, maybe, so you put a ball in between. You put two motors. These two motors. Oh, I'm not showing it on the screen. Sorry about that. So this is what I was talking about. So we get two motors, one right here, one right here. We spin them at certain velocity, and then we just put a ball in between them, and it launches. So if you want to see how well this thing works, I mean, it's pretty obvious how well it works, but, and there you go. You just launched it. So that's what we're trying to imitate with this, with the ping pong ball, basically. So we're just gonna downsize this thing. Smaller motors, smaller battery. We're not gonna need that much juice to launch a ping pong ball since they're very light. So I think that is our winner. So that's good. We chose our design. So I'm gonna go over here so that we have a clean space. Let me see. Sorry about that. So we chose, what step is this? This is mechanism. So this is our shooting mechanism. So let's start off with that first. So this is our shooting mechanism. Like that. So let me draw it out so we have a better idea of how it looks. Should I draw the ping? Yeah, I'll draw the ping pong ball first. So it's the ping pong ball. It's three-dimensional. And then we have the pipe, PVC pipe, more than likely. So I guess I'll put it like over here. I don't know, something like this. It's the PVC pipe, or whatever pipe we're gonna use. And then we're gonna go over here to draw like a wheel. Something like that. This would rotate in this direction, and then on this side there'll be another wheel, and then this would rotate in that direction. And then we just simply connect these to some motors, something like that. There'll be a motor right here. So we have our plus lead, our minus lead, our plus lead, and minus lead over here. And then, that's how we're going to do it. So that is our shooting mechanism. I mean, the best one we have so far. If you guys have another way to launch a tennis or a ping pong ball, let me know. So that is done. Wow, that took a long time. But it's gonna, I think in the end, it's going to save us time. Hopefully. Okay. So we did that. We rated, so I think we can actually cross this out being done. When I cross it out, I mean, we could come back to it later if we need to. So we finished the shooting mechanism. Now, we said that was number 1 to do. Let me not cross that part out. So we finished the shooting mechanism. Next one, power transmission, power source. Let's see what our choices are. I think I already said which ones I think we should use. So the different power sources that are available, pretty common. Is going to be some sort of mobile battery, usually probably a 9-volt to have enough power to drive these motors, or enough voltage potential to drive these motors. So there's that. There's a wall outlet, pretty simple. But the only thing we need some sort of transformer, also some sort of rectifier, regulator, voltage regulator. To do that, that's not the point of the project. We're not here to design a power system for this thing, so that's why I'm kind of straying away from that. Unless we could reuse a power brick. I don't have one near me, but those little wall plugs that have like a brick connected to them. That usually has all the rectification, all the safety stuff, voltage regulation, all that stuff. We could just basically take that, splice the end, and have that as our connection to our device. We could do that, which if we can, we should. We also have a DC power supply, which is not an issue because we could. The robot's not going to be moving. It's going to be stationary the whole time. The only type of movement it's going to have is rotation along its horizontal and vertical axes. So you have full range of motion without translation, if that makes sense. So that's why, since the ping pong bot is not going to be moving, we can use a DC power supply, which is highly convenient. I have one, so we can just use that. Not an issue at all. So, that being said, I think we should just stick with the DC power supply. There's nothing wrong with that. So I'm gonna stick with that because it's probably the most general use of all the power supplies. And if we need a switch to use a wall outlet, um, that's not too big of an issue. The only problem is that we need to find a wall outlet plug that can give us the right power specifications that we need for the project. We can use a 9-volt battery as well. It doesn't really matter, to be honest. Uh, Again, if we start off with the most general case being a DC power supply, we could always downsize it or upgrade it to another power supply as long as it gives us the same power specifications. So that's why I think we should just stick with the power supply. So I'm gonna circle that because it just makes sense in my opinion. If you guys have any other reasoning, feel free to let me know. Where did it go? Okay. So right here, I'm just making sure everything's like outlined so I don't get confused on what we chose and what we're doing. So power supply. Well, it's power supply and transmission, so we'll put that in there as well. Here we go. I guess we can't do that. Okay. Okay. So power supply. How does that look like? It looks pretty much something looks like this. Something. Excuse my drawing skills. Something. No. Okay. I can't draw. But those are like the display. This is like plus ground. Our common ground, and then minus, and then something like a little display like that, and then like that, and then this just goes to any other wall plug, something like that. So DC power supply, that's essentially what this is. Supply. Okay, so yeah, see, it gets easy once we choose our mechanism. Like, that's the defining thing about this whole project. Once we choose our mechanism, then everything seems to fall into place. So power transmission. We didn't do that, I realize. What type of power transmission we're gonna use? Power transmission, if you guys don't understand what I'm saying about that, it's not like a transmission in your car. Or you can think of it in terms of an analogy. It is a transmission in your car, but it's really the actual, like, use of the words, power transmission, meaning how you're gonna transmit the power from the power source to the rest of the device. Obviously you're gonna use wires or something like that, but I mean, like, what are the actuators? What are we trying to do? It's gonna be DC motors, based off this design. So we have 2 DC motors, and then we're gonna probably send it off to an Arduino as well, a Raspberry Pi, simultaneously. So stuff like that. So we could just write those down. We don't need to draw them. So we'll put so plus DC motors. What else did I say? I forgot. Arduino, or a controller, some sort of microcontroller, and Raspberry Pi, and then what else? Camera. So this is how we're gonna. well, maybe it's not really transmission. This is like where the end source is going to be, but our transmission is really just wires. That's pretty much it. So camera. So that's what we're gonna be using. If you guys don't know what the camera is used for, I'm trying to make it have live video feedback. So when someone controls the ping pong ball shooter over the internet, it is you guys can see where the ball is going to potentially land. So power transmission is done. Position control. This one's also pretty much done as well, to be honest. We went over position control previously. So we could build our own design. It's not necessary though. It really isn't. We could just buy this thing and just attach it to our design, whatever we build. So that's pretty much that. Again, if you guys think otherwise or have another suggestion, let me know. So we're just gonna use this. Control-J. Yes. Damn it. Okay, Can I do it again, please? Okay, we're good. Okay, so I'm gonna move this. Not that. Okay, well. Alright, I'm not gonna. I'm sorry about this. I'm not very prepared for this. Okay, so. Position control. What is the next step? What is it gonna look like? It's basically a rotating platform on top of another rotating platform. So we have rotation in this direction, which is like it's a plate, right? Or a platform. So something like this. So that platform rotates, and then we need to rotate in this direction as well. We put this on a platform. I know it's gonna get a little convoluted, but and then this thing is attached to some rail or support, and then this has its own rotation. So something like that, if that makes sense. So we can rotate. We could essentially just rotate in this direction or that direction, and then on this one we're able to rotate in this direction. So that should give us all our possible degrees of freedom that we need. Pretty self-explanatory. So essentially what we're going to do is basically put the did I do this wrong? I think I did this wrong. Yeah, I did do this wrong. I'm very sorry about that. Okay, hold on. Let me see if I could fix that. So how it's gonna look, something like this. This is how it's gonna look. So we have basically a bottom platform. I don't really have to redraw this thing, but I think you guys get the point. We have some rotation in this direction. This would be some sort of motor or stepper motor. So now we're allowed to rotate in the horizontal plane, or along the horizontal plane. So we're able to rotate in this direction or that direction, and then on this platform we're gonna rotate again, but vertically. So we want to rotate in this direction. So if we put something like this here, and then I don't know, a plate here. I should have chose a different color. Sorry about this. This is very sloppy of me. Change the color. So we'll just connect that, put a plane here. Let me make it bigger. Something like that. So now we should be able to rotate in the axes we need. So we'd be able to rotate in that direction or that direction. Okay, does that make sense? And then we put the actual mechanism, the shooting mechanism, on this plane, preferably in the middle, and then aligned in this direction. So that way, you should be able to rotate, choose a direction, and then tilt. Pretty self-explanatory, I think. I think the picture doesn't do as much justice as this image. Okay, so we're done with position control. Yeah, we're pretty much flying through this now since we chose our mechanism, which makes sense. There we go. What else are we gonna need to do? Store this ping pong balls. This is the next difficult part. This one goes hand in hand with the shooting mechanism. So we may need to come up with a new idea or just stick with one of these. Okay, so we gotta really think about, it's already 8:30. I'm very sorry, guys, to cut you off that quickly, but if you're still watching, it is 8:30. I didn't expect it to be 8:30 already, but we got pretty far. I'm gonna end the stream pretty soon, simply because I gotta go to work tomorrow and I'm pretty tired. But what we did today, quick overview of what we did today. We basically went through this whole mechanism or the whole list and choose our best designs out of each list. We haven't gone through all of them. We've done 3 of them today. Hopefully by tomorrow we'll finish these up, and then from there we could actually do some designing work, at least virtually, and then see what we actually need, then create a parts list, and then hopefully start building once we get that parts list correct, or as best as we can get it, and then buy the stuff, start building, probably start programming as well, and then we'll be potentially done with the whole project. I don't know how long this is going to take, but we got through a lot today. I think we made great progress. So we got the shooting mechanism done. We chose the tennis ball shooter. I wish we got the solenoid one. I really think there is a solenoid out there for our application, but I can't find it. And I don't want to risk it too. I don't want to buy it and then not use it. So let's stick with our safe design, and it's gonna be this one. For the shooting mechanism, for the power supply, again, DC power supply. We could change it later if we need to. And then for position control, probably gonna buy this. Pretty self-explanatory. It's just stepper motors rotating on different platforms, which gives us the ability to rotate and aim. So that is it for today. If you guys are interested in watching more of these streams, I stream Monday, Tuesday, Wednesday from 6:30 to 8:30 PDT Los Angeles time. That's nighttime. Well, 6:30 p.m. to 8:30 p.m. Los Angeles time, or Southern California. So if you guys want to watch that, if you guys can't catch the stream, then the streams are available on my YouTube channel. They are archived, and feel free to watch them all you want. There'll be timestamps to give you guys if you guys want to see a specific location or a specific part of the video. There'll be timestamps so you guys can watch it. So with that being said, I think we're done. I'll see you guys tomorrow if you guys are going to be watching tomorrow.